Hi everyone. So just recording my video for homework 5. I'm gonna do problem 4 because they were all like pretty long and challenging, but this one was probably the most interesting to examine. So first of all, the system we're looking at is some mass hanging vertically from a nonlinear spring. So we're given our equation of motion already, and we're given the potential energy of the spring defined by this function Vy. And then obviously then when that becomes a force, we know that's going to be the dv dy of the system. So we start off with our entire equation of motion already given to us. There's also some dampening force involved in this Vy dot term. So first of all, we need to non-dimensionalize the system, which is just gonna kind of pile together all of our unknowns into less unknowns, and then it'll hopefully be easier to solve. So first of all, I find what the dv dy was. Pretty easy, just a bunch of polynomials, so that just becomes mg k1y k2y. Plug that into our equation of motion, and we end up with this. That's what my double dot is equal to. So to non-dimensionalize, first we're gonna take our y and we're gonna say it's equal to some L times x, where L is whatever parameter makes the system have no dimensions. And we're gonna do the same thing for time. We're gonna say that t is now equal to some capital T times some parameter, some value. So from that, we can define our derivatives with respect to time. We can say that dy dt is gonna be the same as x dot times this L over T, because it's the coming from defining T in terms of this capital T. Then if we go ahead and repeat that process and take the derivative with that of this with respect to time again, it's just going to look like adding another 1 over T term coming over from the fact that we're technically deriving by this value instead of the T now, because it's a non-dimensional equivalent, whatever that means. So we can start by just taking our equation of motion, and everywhere we see like a y double dot, we replace it with an L over T squared. Here with this y dot, L over T x dot, etc. Just kind of, we have a normal y, so that needs to be an LX. And then this y cubed is going to be L cubed S x cubed. So then the next step was to isolate our acceleration, and that just kind of simplifies the problem, puts it in a nicer form. We go ahead and divide everything by mlt squared, which here it's going to leave us with this bt over m, where they have a t squared over l, t squared over m, and then l squared t squared m as like our coefficients. And we know in this problem we're kind of helped by the fact that we know that x dot has to have a coefficient equal to 1. So we can take this bt over m term, set it equal to 1, and from that we can solve what our t should be to non-dimensionalize the system. It should be defined as mass over the dampening. From there we can also do the same thing for this x cubed term. We know that this bid k squared l squared t squared m has to equal 1. We solve this out for L squared in terms of M, T, and K. Then we go ahead and plug in our definition of T as M over B, and we end up with this parameter as equal to the squared. We square root it. We get that L is equal to B over square root K over M, which I think was actually, it was given to us in the problem. But from there, we're able to reduce our system into the form that they talked about. Or we're able to reduce the system in such a way that we can name this parameter A and we can name this parameter H, and it'll be in the form that they gave it to us. We can just kind of make that substitution. Then I went ahead and wrote a little program to just plot the phase portraits of the system. And what we can see is that at a negative 1, we have a single stable spiral at 0, 0. But when we increase a to 1, we see a change in where our zeros are. Now we have two zeros here, and they're both stable spirals. And then at 0, 0, we actually have an unstable spiral of the system. So I think that's a bifurcation. So then we need to go ahead and put the system into state space. That's just, in this case, you just define x dot equal v, introduces variable v, and then we can turn our second order into a first order. V dot is equal to negative v plus ax plus x cubed plus h. Then to find the equilibrium, we set both of these to 0. Since this equation, x dot is equal to v, only has a 0 at 0, we know that v has to be 0. So now the rest of our roots are going to depend on this third degree polynomial. Some x star cubed minus a x star minus h is equal to 0. Which is, where these come from. As if you graph the polynomial, you'll see that as you increase this a, it goes from having a root at 0 to 3 roots, kind of spreading out. Then we need to take the Jacobian of this second degree system. So there is no x here, so this is a 0, there's just a v, this is a 1. Then the derivative of this with respect to x is going to be a minus 3x squared. And then with respect to v, it's just going to be that negative 1. So from the Jacobian, we can first see that our trace is negative, which means that the only instability we could have would have to come from a saddle point, which would imply like our determinant in this case, just 3x squared minus a, would be less than 0. That's the only instability, because since the trace is negative, any other point will be stable. Then I went ahead and generated this bid plot that's essentially just showing a over what our x star root is. So we're like solving out that polynomial based on what a is, and then we're determining if that would be stable or unstable. And what we see is that for an sorry about that. For a less than 0, we start as a stable spiral. We have a bit of a stable node moment, and then we go back to being a stable spiral for like a less than 0 or any positive roots. But for any negative roots, we at a high positive a, but a very negative root, we're going to be still stable, going to that node. But at the moment that a is equal to 0.087, and we have a z root of negative 0.171, we actually have a saddle point now, especially as we're approaching 0. You can see how we form this saddle point at our 0, 0. That's this red term here, forming whenever AC crosses this threshold. And I mean, that's essentially what I said here, a bit fancier and more well rehearsed. But so, anyways, that was my solution to this problem. It was a long-ish problem. It was just the graphing of the saddle points took a little long. There was just more thinking about like, we need to solve our root, and then we need to plot for all these different values and kind of what are we looking for. We need to define stability through the Jacobian and stuff. But overall, that was my attempt at the problem. Please let me know if you noticed that I messed anything up or said something that was wrong. Thank you.